Welcome viewers to the first lecture for the online series of lectures for the course of General Relativity. In the supplementary lecture, we discussed the basics of topology. It was an optional lecture, meaning that you can skip the lecture if you feel it's not needed. Today's lecture is dedicated to multivariable calculus. By going over the lecture, you will have an understanding of how to do calculus on R to the n. So let's get started with multivariable calculus. Basics of multivariable calculus. So we'll get started with an example. Consider this function from R2 to R defined as follows. It's a piecewise defined function given by xy divided by x squared plus y squared when xy is not the origin. Okay, so when this point is off the origin, then this formula holds, and when it's at the origin, this is simply 0. Okay, this is how we define this real valued function on R2. Okay, so now let's study this function a little in detail. Okay, so what happens along the x-axis? Okay, so this is a two-dimensional plane. Okay, so the coordinates of the two-dimensional plane x and y. So along the x-axis, so I'm trying to study the behavior of this function along the x-axis, where y is identically equal to 0. Okay, so here this guy is 0, right? Because y is identically 0, so this is 0 for all x taking values in the set of real numbers, right? We can see it from here, right? When x is non-zero, this formula holds. Okay, and we plug in y to be 0 since we are walking along the x-axis, so y have to be plugged in to be 0, and this guy is 0. It makes sense because x is not 0, so that this denominator is not 0, but the numerator is 0 since y is identically 0, and this guy is 0 for x being not equal to 0. And when x is equal to 0, this is 0. This formula holds. So this guy is identically 0. That is, f is constant and identically 0 on the x-axis. Okay. So if the function itself is constant, and which is in particular is 0 along the x-axis, so its derivative is also 0, because the derivative of a constant is also 0. So from which we see that the derivative of the function at the point y equal to 0, at the points on the line on the x-axis, is equal to 0, identical. Okay, so this is the behavior of the function along the x-axis. What happens along the y-axis? Let's see. So where x is identically equal to 0, so it can be viewed in the similar way that f0y is equal to 0 for all y in R, okay, using the same reasoning that we did for this case, okay. That is, the function is identically 0 along the y-axis, therefore the derivative must also go to 0, okay. So that the derivative of f with respect to y on the y-axis, where x is identically equal to 0, is equal to 0. Okay, so thus we see that both the partial derivatives del f x and del f by del y, both these partial derivatives exist at 0, 0, right? And are equal to 0. We have seen that they are both equal to 0 at 0, 0. Okay. Now, so we have seen that these two partial derivatives exist at 0, 0 and they are equal to 0. Now we are going to show that this guy f is not continuous at the point 0, 0. This is what we are going to show now. Okay, let's see how we find that the function f piecewise defined, as discussed earlier, is not continuous at 0, 0. Okay, so now I want to draw a picture of this of the domain plane, the xy plane, and this origin is 0, 0. So I'm studying, I'm concerned with the behavior of the function at the point 0, 0, and I want to approach this point 0, 0 along the y-axis and also along the x-axis and also along the line given by y equal to x, which is at angle 45 degree with the x-axis. Okay, so I'm going to approach this point 0, 0 in these three directions. So let's see what happens then. So so let's consider the line y equal to x and try to evaluate the limit. Try to evaluate the limit of fxy as xy approaches 0, 0 along this line. Okay, so so let me write down the function here, which I have erased. The piecewise defined function xy divided by x squared plus y squared for xy not the origin and 0 identical and 0 when xy is the origin. Okay, so now I'm trying to find the limit of this guy. Okay, so the limit, since x and y are equal along this line, so I'm just writing x to approach 0 because y also approaches 0 since x is equal to y, and here I plug in x to be equal to y, right? Because I'm always on this line. So that gives me x times x in the numerator, and in the denominator I have x squared plus x squared. So that this is simply lim x approaching 0, x squared divided by 2x squared is equal to 1/2, which is not equal to 0. Okay, all right. So we have seen that, therefore lim xy approaching 0, 0 f of xy is equal to 0 whenever we approach 0, 0 either along the x-axis or along the y-axis. So this guy is 0 for both x and y-axis, for both x and y-axis, right? So if you approach 0, 0 lying on both x-axis or y-axis, you get the limit to be equal to 0. Okay. This is what we have seen earlier, and we have seen that if we find the limit lying on the line y equal to x, the limit is 1/2. Okay. So what does it mean? It means that we are getting different limits, limiting values of the function when we approach the same point along different paths, which means that the function is not continuous at the point 0, 0. The function fails to be continuous at the point 0, 0, so it cannot be differentiable at this point. Alright. So what did we find? We found that although both the partials exist at the point 0, 0, the function fails to be differentiable at that point. So here is the conclusion that we can draw from this example. Therefore, mere existence of partial derivatives of all orders don't guarantee differentiability at a given point. Of a given point. Sorry, differentiability at a given point. Okay, so in other words, differentiability at a given point is a much stronger condition than the mere existence of the partial derivatives at that point. Okay, now let me define something here. Let me define differentiability first. Okay, what does it mean by a differentiable function? So for that, we'll do things step by step. So first we'll consider functions, okay, whose domain is a subset A of R to the n. Okay, this is the Euclidean space of dimension n. Take a subset of R to the n which is going to be the domain of the underlying function, okay, and whose ranges is going to be R, the set of real numbers. Okay, so now some notations. If f is a function from A to R, where we have already described that A is a subset of R to the n. So if f is such a function, okay, then we denote f of vector x, okay. So it's cumbersome to denote this vector, write this vector every time on x. So I think I'll keep it for the moment, but later on I'll get rid of this vector sign. So f of x, vector x, is f of x1, x2, all the way up to xn, because vector x is designated by this n tuple on this vector space R to the n. Okay, right. So what is this guy or this guy? This is a real number, okay. This is a real number. It takes value in the set of real numbers, and x vector, which is the same as this n tuple, okay, is a point in the subset of R to the n. Okay, now so R to the n is a topological space that we have discussed in the first lecture, okay, the Euclidean space. And now we choose an open set U from this Euclidean space of dimension n. Okay. So now we just replace with the arbitrary subset of the Euclidean space with an open set U. Okay. So with f now being a function from U to R. Okay. Now at each point, a vector A in U in the open set, the partial derivative del f by del xj evaluated at this point in the open set. So the partial derivative of f with respect to xj, okay, xj is one of the coordinates of the vector x. Is of course the following limit, if it exists. We already know that. Following limit if it exists. Okay, so what is the limit? So we write del f by del xj evaluated at the point vector x is equal to vector a, right? Is going to be the limit of some expression, some rational expression as h approaches 0. And what is the rational expression? F of a1, a2, then aj plus h and all other coordinates stay the same. F, A1, AJ, this is dot dot. This is dot 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 dot. Then AJ and finally AN divided by H. Okay. So if the limit exists, then we say that the partial derivative of f with respect to xj exists at this point a, and that is given by this expression. Okay, let me erase now. So now if this partial derivative of f with respect to xj is defined, that is, if the limit above the limit mentioned earlier in the previous slide exists at each point of u. So if this guy exists at each point of u being the open set of r to the n, for all j between 1 and n inclusive. Okay, then we get n functions on u. Okay, because as we vary j from 1 to n, we get n functions. We obtain n functions on u. Okay, and then we say that okay, alright, so as we vary j from 1 to n, we get n functions. So we want these functions to exist at all the points of this open set u, and we also want these functions to be continuous. Okay, so these partial derivatives exist, these partial derivatives, these n functions exist, and they need to be continuous at every point of this open set u. And only then we say that f is continuously differentiable on u, and we denote the fact that f is continuously differentiable on u with the notation f belonging to C1 of u. Okay. So let me repeat. When all the partial derivatives, the first order partial derivatives of f exists, and each of them is continuous in the open set u, we say that the function is continuously differentiable on the open set u. Okay. All right. So now we shall say that f is differentiable. F is differentiable at a given point a of the open set u if there is a homogeneous linear expression. This is a homogeneous linear expression. Okay. So here you see that this a vector is given, whose coordinates are given by ai's, okay, I running from 1 to n, and we are talking about an arbitrary point x whose coordinates are given by xi's, and there are certain constants called bi for which we can write this homogeneous linear expression such that the inhomogeneous linear expression inhomogeneous linear expression, because I have a constant term added to this homogeneous linear expression, it becomes inhomogeneous. Then this guy is supposed to approximate fx near a in the following sense. So by a limiting expression, we'll see how this guy approximate fx. So the limit as x, the vector x approaches vector a, the rational expression that I'm writing now goes to 0. F of vector x minus f of vector a minus this homogeneous linear expression bi xi minus ai divided by the norm of this vector. Okay. We know the norm because this Euclidean space is equipped with the standard norm, okay, induced by the metric. This goes to 0. Okay, so this expression goes to 0 as x approaches the vector x approaches vector a, and then we'll see that this inhomogeneous linear expression actually approximates f of x. Okay. All right. So I want to state it a little more formally now. So what is the formal statement? If there exists constants bi's, okay, that I mentioned earlier, n constants, and a real valued function are of vector x and vector a defined on some neighborhood v of a in u, which satisfy the following two conditions, okay, the following two conditions. What are those conditions? The first condition being fx is equal to fa plus this homogeneous linear expression bi xi minus ai plus the norm of vector x minus vector a times the remainder, this guy. Okay, so it's evident that this guy So what we had written earlier in the previous slide, that the limit of the rational expression goes to 0 only if we have also the limit of this remainder thing approaching 0 as x approaches a. Okay, so these are the two conditions. So these, I'm not going into the detail, these BIs, these n constants are uniquely determined and are basically the partial derivatives of f with respect to the xi's. These are uniquely determined, and these are nothing but the partial, these numbers, these constants are the partial derivatives of f with respect to the coordinates evaluated at the point a, at the vector a. Okay, so if we replace these VI's with these partial derivatives, then this reduces to the following final expression for the multivariable function: I equal to 1 to n del f by del xi evaluated at the point a times xi minus ai plus the norm of x minus a times this real valued function. Okay. Okay. Okay, so this is the conclusion. Actually, existence of partial derivatives along with their continuity guarantees differentiability at a given point a in Rn. Okay, so we need existence of partial derivatives plus continuity of partial derivatives to guarantee differentiability. Okay, good. Now I want to state a few words about chain rule that is very important in the context of multivariable calculus. So let me get started with the chain rule for the simplest case. A few words on chain rule. Okay, first we need the idea of a differentiable curve in an n-dimensional Euclidean space. Okay, so we need the idea of a differentiable curve in Rn. So by a differentiable curve in Rn, we mean a function f from the open interval ab to Rn. Okay. So whenever we have a differentiable curve in Rn, we'll start with a function from an open set ab to Rn, r to the n, with see that f of t. Okay. So since this is a function of a point that resides in this interval, that 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 parameter is denoted by t, and this ft, what is this? It's a vector in Rn, so it has n components. Okay, so we're gonna have an n tuple here, and each of the coordinates of this n tuple will be a function of t. Okay, x1t, x2t, all the way up to xn t, right? Okay. So So since we are talking about a differentiable curve, we will have a function like this, and we demand that each of these n coordinate functions are differentiable on AB, are differentiable on A comma B. Okay, so these are the usual functions that we study in single variable calculus, right? Because these are real valued functions on the set of real numbers. These are functions like xi's are functions like from R to R, right? So in this special case is like from the from the open interval AB to R. Okay, so we already know how to study such functions from our knowledge of single variable calculus, and we know that differentiability for the case of a function of one variable, existence of derivative implies differentiability. Okay, it's pretty simple in the context of single variable calculus. So if the derivative exists, then the function is differentiable. It's not that simple in the context of multivariable calculus. We have seen there all the first order partial derivatives should all exist, and they need to be continuous at the same time for the function to be differentiable at a given point. All right. Okay. So we have seen that. So it's immediate from here, from our discussion, that these xits are real valued functions of one variable, are real valued functions of one variable. Okay. So I assume that you are all familiar with the CR differentiability of real valued functions of one variable. If you are not, let me recap. So say that we dealing with ft equal to t to the 1 over 3. So how does the graph look like? The graph looks like this. Okay, this is the graph of ft is equal to t to the 1 over 3. This is t, this is ft. Okay, so this function is continuous at the point 0, 0. At the origin it's continuous, but it's not differentiable at the point 0, 0. Why? Because the tangent to the curve at the point 0, 0 is vertical. Okay, so the derivative does not exist at that point. So it means that although f is continuous, it is not differentiable, because it fails to be differentiable at the point 0, 0. Okay, so now, for example, take the function ft equal to t to the power 4 over 3. Okay, so now the first derivative will be 4 over 3, right, t to the 1 over 3. Okay, and we have already studied that this function is continuous, but this guy is not differentiable, right? So the first derivative is continuous, but the first derivative is not a differentiable function, meaning that ft is equal to t to the 4 over 3 is c1 but not c2. Okay. So you can go on forever like this, creating new functions and study CR differentiability for real valued functions of one variable. Okay, that's sufficient. Now I want to mention a few points with bullet points. Some important facts. F is a CR differentiable curve on AB. So we know that how to talk about the CR differentiability of each components of F, right? That we have studied earlier, because the components of this function F are real valued functions on the interval AB. So now F is a CR differentiable curve on AB in the sense that all the n coordinate functions xi t's. Okay, remember that we have written down ft as this n tuple, right? x1t, x2t, all the way up to x and t. Okay, and these xit's, all the n coordinate functions xit's as real valued functions on R of class CR. Okay, so whenever each of these coordinate functions are of class CR, we say that this function f is a CR differentiable curve on AB. Okay, so that was the first point. It is a CR differentiable curve on this interval AB. Second point is, for any value t0 lying in this interval AB, and f function which was chosen to be the CR differentiable curve on AB is mapped to an open set of R to the n. Okay, now I erase that part. Okay, so okay, let me rewrite it. So and f is this function from AB to the open set on R to the n, and G is a CR differentiable function on U to R. Okay, that is G is a function from U to R. Okay. And which is this guy G is taken is differentiable, is taken to be differentiable at ft0, which is in U, right? See that f is a function from AB to U, which is an open subset of R to the n. So ft0, where t0 belongs to this interval, then ft0 is of course in U. Okay, and G, the function G, is taken to be differentiable at this point ft0. This is important. So now, what is this composed function? G composed with f. So f is a function from AB to U, and G is a function from U to R. So G composed with f is a function from AB to R, right? An ordinary function from something like R to R. Then this composite function is going to be differentiable at t0. t0 is a point here belonging to this interval. So this composite function will be differentiable at this point t0, and the derivative of this composite function and the derivative of the is given by the derivative of this guy is given by the chain rule, the famous chain rule. Okay, G composed with f, because it's a function of one variable, so it's the total derivative of G composed with f, and it's going to be evaluated at the point t0. Okay, since this function is differentiable at t0, so the derivative is given by this sum. Okay, so first thing is to take the derivative, the ordinary derivative of the components of f. Okay, so what were the components of f? So let me rewrite this part. F is a CR differentiable curve on AB in the sense that all the n coordinate functions excites as real valued functions on R are of class C to the R. Okay, so now see that you write ft as this, right, as this n tuple x and t. So now each of these components, or the coordinate functions, is just a function of t. Okay, so now you take those components and take the derivative with respect to t and evaluate the derivative at the point t0, and then multiply it with the partial derivatives of these functions g, of this function g. Okay, since g is a function from u and u is a subset of R to the n, so there are how many coordinates involved? Okay. The coordinates involved are xi's. There are n coordinate functions, so we're gonna take the derivative of g, partial derivative of g with respect to this xi's, and evaluate this at ft0. So this is the chain rule. Okay, you know, for this f being a CR differentiable curve on AB and G being a function on a subset, on an open subset of Rn to R. Okay. Okay. So this was the first step of the chain rule. So this guy, this is the chain rule for real valued functions. Okay. Okay. Good. Now we can generalize this idea to functions of subsets U of Rn. Now we can generalize the idea to functions on subsets U of R to the n. Okay, so the domain will be subsets U of R to the n, but whose range is no longer R but in R to the m. So that is, we consider functions like f from U being a subset of R to the n to V being a subset of R to the m. Okay, so we'll be considering this such function. So we need to fix a few notations. So write this a vector x by this n tuple, and which is going to be a point in this open subset of R to the n. And what is f of x? F of x is going to be a point here, which will be an m tuple whose each of these component is going to be a real valued function on U. Okay. Fm vector x. Okay. Okay. So note P in U is a fixed point. By fixed I mean that it's a given point. Okay. Fixed point with coordinates P1, P2 all the way up to Pn. Hence, Fp is in V is also a fixed point with coordinates F1 vector P, F2 vector P, all the way up to Fm vector P. Okay, so here it is. So when we are given a variable point in this open set, we're going to denote it with vector x and its image in the open set V as f of x. So we have a particular point in this open set that we are going to denote by vector p and its image under this function f as this m tuple. Okay, good. Conversely, any set of f functions, so it's the other way around, any set of f functions f1, f2, all the way up to fm defined on u being a subset of r to the n with values in R, meaning that each of these m functions are defined on u being a subset of r to the n and 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 taking values in R determines the mapping f from u to v, whose components will be precisely be these functions. Okay. Okay. Now we take another function g. Now let g be another function from the subset v of r to the m to r to the l. Okay, it's another function. Now write a point, write a point by vector y, which is an m tuple, a variable point on this in this subset. Okay, ym being a point in this open subset V of r to the m. Okay, so then g of a vector y, right? G is defined on this open subset V of r to the m. So g will be a function of vector y, and it is mapped to r to the l. So there will be l components of this function g. Let me write them: g1y, g2y, all the way up to gl y vector. Okay, so that we see that each of these component functions gi are maps from v to r, so they are just real valued functions. So that now gi composed with f. Okay, so gi is a function from v to r and f is a map from u to v. So it means that the composition is a map, right, from u to r. Okay, now the chain rule for such functions. So I'm not going to prove these theorems. I'm just briefly mentioning the results from the multivariable calculus, important results. So so this is a function on this open subset of R to the n. Okay. So the variables, the variable point, a variable point in this open subset U was denoted earlier by vector x, right, whose components were these n tuples, remember? So now this guy, so the partial derivative of this function with respect to xj, okay, where j are the n, xj is one of the n components of the vector x. Okay. And then I'm going to evaluate it at the point p vector. You remember the fixed point that we denoted by p vector, okay, which was the fixed point on this set U, right? We erase that part, but if you go back and check that P was taken to be a fixed point in this open set U. So we evaluate it here, and this is going to be equal to a sum where over k, where k runs from 1 to m. So here we have the partial derivative of, so this function, so this function has how many components? This function has n components, okay? So I'm going to take an arbitrary, so one of the components here, f to the k, no, not f, fk, okay, fk, and take the partial derivative of fk. So a point here in U is given by x, right, which is nothing but this n tuple. So I'm going to derive fk with respect to xj and evaluate it at the point P, okay, and then you take the other function in this composition. You're going to derive this guy. So you see that each of these gi's, right, are function of y's. So you want to derive this gi's with respect to yk, right, where k runs from 1 to m, okay, and this is going to be evaluated at fp, right? Remember that fp is an element, fp is a point in the set V, okay, and since gi, for each I, gi is a map from V to R, it makes sense to evaluate this derivative at the point fp, right? Okay, so this is the chain rule for such function of several variables, okay. Okay, so I think I'll take a break here, and in the next segment I'm going to discuss differential of a map, okay. So in the next segment we are going to discuss about the differentiable differential of a map F from U being an open subset of R to the n to a subset V of R to the m. What does it mean by differential of such a map? We are going to discuss in the next segment. Thank you for attending the first segment.